Hey gang, I'm back again. Okay, so now we're going to talk about deorbiting. So if you're on the orbiter and you're going in the orbiter around Venus, how do you get off of the orbiter? Many of you remember that when I said that you have to deploy from the orbiter. You have to deploy from whatever vehicle you're from. You can't just fall off of it. If you're on the orbiter and you're not forcibly deployed, you will not deorbit. You'll just sit there next to the orbiter. And then it's awkward for everybody. It's awkward for the orbiter, it's awkward for the payload because, So you don't want to do that. You just want to avoid the awkwardness at all costs. So in a previous lesson we talked about orbital velocity. We're going to recall some equations from that lesson or from that lecture, whatever, that video. So, but right now we're going to talk about deorbit and impact. You can follow along on page 65 in your InSPIRESS notebook. It's this page right here. This page has got a lot of words on it and a lot of stuff in it, but it's not as bad as it looks at first glance. So when you're in orbit around a planet, if you're standing on the planet and looking up, it basically looks like the thing that's in orbit around the planet is just going straight overhead. So that's what we're going to assume right now too. We're going to say, okay, this is our surface, and this is our little mass orbiting. And so basically its entire velocity is in our x direction. We're going to define y is up and x is to that way, whatever that way is. So the velocity of the spacecraft is going in this direction. And vector-wise, it's just a single arrow that's pointed in that direction. So it's all in the x direction. Everybody follow so far? So you'll also remember from our equations that from our orbital velocity lecture that there's a balancing act of gravity and circular motion force that keeps the orbiter at this altitude. So we have F sub c, which is the force due to circular motion, is equal to the force due to gravity, right? And then equation-wise, mv squared over r, that is F sub c, equals the force due to gravity is big G, big M, little m over r squared. Where in this case, r is our, this is just our altitude above the surface, this distance. R is all the way to the center of the planet down here. So that's r, it's a different number altogether. I'm off camera. Don't let that fool you. If you have questions about this, go back and watch the orbital velocity lecture and it'll explain this. But these two equations, this relationship is going to tell us how to deorbit, essentially. So, and then of course, to solve for velocity, velocity is the square root of big G, big M over R. Remember, little m is the mass of the orbiting thing, big M is the mass of the planet being orbited, and big G is Newton's gravitational constant. So, how do we deorbit? Let's look at it again over here. So this is the velocity. This is our velocity vector for our spacecraft, just going straight in the positive x direction over the surface of the planet. What we want to do is we want to unbalance this balanced equation here. We want to make sure, we want to have gravity pull us down. So how do we do that? We say, and there's only certain things that we can play with, really. We can play with the velocity and the radius. Messing with the masses, we can't mess with the mass of the planet, that's for sure. Can't mess with Newton's gravitational constant. You don't want to mess with the mass of your orbiting thing because it falls out of the equation, if you remember that. It cancels out, right? So we really only have velocity and radius to kind of play with. So if you think about your velocity of the spacecraft at a certain altitude above the surface, here's our surface, and here's our altitude. And the planet's radius is going to be constant. So just think of so here's the planet's radius. Just think of our altitude as being the way that we change this part of the equation, okay? So here's our little mass, and it's moving. So what if we were to slow down if we're at a certain altitude, a certain r, and we were to slow down, what would happen at that point? If our spacecraft were to slow down, or if our spacecraft were to force our payload to slow down, what would that happen? Basically what would happen is the velocity would decrease, which would decrease this F sub c, which means that gravity would overpower F sub c. Gravity would be like, I have you now, and ha ha ha, start pulling you down because there's no velocity term in this part of the equation. So one way to deorbit is to decrease velocity at a given altitude. So how do we decrease velocity with the vectors? Remember that? Vectors are tip to tail, or at a tip to tail. So all you do is you shoot backwards, essentially, a certain amount of velocity. So the orbiter is still going this way, and the orbiter just kind of goes like this, just shoots you backward. Hey, see ya. And that's what it does, is it shoots you backward. So now you're traveling with this velocity, and you're at the same altitude, essentially, but your velocity is too slow to maintain that altitude, so gravity takes over and you start to fall. So you've got this, so you're at this altitude, you're at this velocity, and then gravity starts to pull you down, and there's your resultant, assuming no drag in this case. So here's your Vx, Vy, and V total as you impact the ground. That is one way to deorbit. Basically, have you shoot yourself backwards. So you're maintaining it's a constant altitude, but you've slowed down basically. So the other way to do it is, if you remember, we have altitude and velocity to play with. So we just played with velocity. Let's play with altitude now, or radius, but altitude is the way we play with radius. So if we were to decrease our radius at a certain velocity, what would happen to this equation? So if we decrease this r, this F sub c gets bigger, right? Because it's in the denominator here. If we decrease this r, F sub g gets a lot bigger because it's r squared. So decreasing r a little bit on this side decreases F sub c a little bit. Decreasing r a little bit on this side is the same radius. It increases F sub g a lot. Did I say decreases? Decreasing r increases F sub c a little bit. Decreasing r a little bit increases F sub g a lot. So the same thing happens again. Gravity is, I have you now, and it pulls you down. So look at it as vectors. How do you decrease with a constant velocity, how do you decrease your altitude? Is you just shoot yourself downward toward the planet. The spacecraft would basically fly over and it would shoot you downward toward the planet. And that's what we're doing here. We shoot you downward, and your resultant vector is there. So here's your Vx, Vy, and here's your V. And again, this assumes no drag in this case. If you have drag, it's a slightly different story, and we will have drag at Venus. But this is how you deorbit. This is how you begin your initial descent to deorbit. And again, it's all based on this relationship, this tug of war between the circular motion force and gravity trying to pull you down. All right, thanks.